questions about anything before we start? How'd the homework go? Just the last 4. Okay. I did not assign 1.3 yet, right? So the last 4 and 1.2?
Yeah.
All right, give me one of them. We'll do one. Okay, what was it?
It was dy over dt equals y.
And what, we're supposed to find a general solution?
Yeah.
Okay. So this is separable. In fact, it's autonomous, right? We only have y's on the right. So I can move this over, so I would have 1 over y times 1 minus y, dy equals dt. Right, and then so I integrate both sides. And this side is obviously t plus c. And the left side, I'm going to do partial fractions, okay, because it is written as a factor. So I'm going to go to a new slide, do partial fractions, then I'll come back and finish integrating. So 1 over y times 1 minus y. So those are 2 distinct linear factors, which means that you can break it up into the sum of 2 fractions, a over the first factor plus b over the second factor. Then you multiply both sides by the LCD, y times 1 minus y. Okay, so over here, the whole denominator cancels and I just get 1. On the right, with the a fraction, the y's cancel, so I'm going to have a times 1 minus y. And the b fraction, the 1 minus y's cancel, so I have b y. Okay, distribute your a. Combine like terms, so I have negative a plus b times y plus a equals 1. Then you match up coefficients on the left and the right. So what's the coefficient of y on the left side of this equation? 0, right, because there is no y term. So I would say that negative a plus b has to be 0. And the constant on the right is a, and the constant on the left is 1. So a is 1, and that means that, what does b have to be? Also 1. A equals b equals 1. All right, so then I can rewrite this thing that I'm trying to integrate as 1 over y plus 1 over 1 minus y. Oops. So this is going to be over here. Yeah. Yep. Yeah. Yeah. You could have separated that into a sum of 2 fractions. Yeah. Yeah. I mean, you definitely can separate that into 2 fractions just with some knowledge of how fractions add. Yeah. Yeah. Okay, so then you can integrate each of these separately. So the integral of 1 over y is the ln of the absolute value of y. The integral of 1 over 1 minus y would be the ln of 1 minus y. But then you have to account for the chain rule when you go backwards. So I have to put a negative here. So if you wanted to do that formally, you would do that with the w substitution, right? Let w be 1 minus y, and you'd end up with the negative in there. That equals t plus c. All right, so now I have the ln of something minus the ln of something. I want to I can combine those into one single logarithm, right? If you remember that from like college algebra or pre-calc. The law is the ln of a quotient expands to a difference, and then you can contract it back to a quotient. Okay. So then, to get rid of the ln, because we're trying to solve for y, raise e to both sides. So on the left side, I'm just going to have y over 1 minus y, because e to the ln of some stuff gives you the stuff. And then this is going to be e to the t plus c, which we do this little trick that we've been doing over and over again. Rewrite e to the t plus c as e to the t times e to the c. And then e to the c becomes some new constant, k. My new arbitrary constant. And then because k can take on every value, positive and negative, I can drop the absolute value bars without putting the plus or minus in front of the k, because that would be redundant. So I just have, right, but you can throw a negative in front of it. The k in front of it, oh, I see. This constant you're saying would always be positive? Dropping the absolute values? Yeah, so in that case, it's always going to be positive. So,
But I guess you can say k is plus or minus.
it's just some new constant, some new arbitrary constant. But e to the c would, no, okay, so if k equals e to the c, this is a good observation, because you're right, I hadn't thought of that. So e to the c is always positive, right? Which means that k is always positive. So when I drop the I can drop the absolute value bars because this thing is always positive. Like, so I'm not dropping it because k can be plus or minus. It's because it's no, k is e to the c. It's just positive. So the absolute value doesn't matter because it equals, absolute value makes something positive, right? And the right side is already positive. So I don't have to put it there. Yeah, I could have dropped it before, yeah. So to finish solving for y, let's see, I'm going to have y is equal to k e to the t times 1 minus y. Distribute. And now I'm going to collect y terms on one side and non-y terms on the other. So add y plus k e to the t y equals k e to the t. Factor out a y from the left. Yeah. Divide both sides by 1 plus k e to the t. So we get y equals k e to the t divided by 1 plus k e to the t. I think that you had one of your classwork ones from the day that we did separable equations was very similar to this. And I gave you also an initial condition, and it turned out, so you would do all this and solve for it, and then when you plugged in the initial condition, you couldn't do it. There was no solution. So I want to get an estimate for y of 0.5 more accurately. So I'm going to draw a little picture. Here's my initial condition, 0, 1. And what is the slope, dy dt, at the point 0, 1, my initial condition. -1. Yep, I plug in 0 for t, -1 squared equals -1. Okay, so I know that I'm going to be moving in the direction, downwards direction, right? And let's mark off like, that looks like about 1. Okay. So I'm just going to take a step 0.5 to the right. Okay, so my tangent line looks like this. I'm moving in this direction, right? To make a slope of -1. But I'm going to use the tangent line as an approximation to the curve. I'm going to say 0.5 is pretty close to this point, which is tangent, right? Right here, I know this point is on my curve. So this point is on the solution, and this is a tangent to the solution. So I'm going to say, well, this is a pretty good approximation of the solution as long as I stay relatively close to this point of tangency. And we're going to call 0.5 relatively close. Okay. So what are the coordinates of this point? Point five. Yep. Nope. I know that this is a straight line, right?
Oh, okay, sorry.
And I have created a little triangle here. I know that delta x is 0.5. I know that the slope of this line is -1, and I'm looking for delta y, right? So I would say delta y over 0.5 equals -1, which means that y has to be, delta y is -0.5. So that's my change in y. I went down by 0.5. And my y started at 1, right? The y coordinate of this point here is 1, changing the y coordinate by -0.5, going down. So I land at 0.5, comma, 0.5. Does that make sense? So we're going to say 0.5, comma, 0.5 is near my solution curve, right? So I would say that y, my solution of 0.5, is approximately 0.5. Does that make sense? Okay. So my real curve, might look like something like this, right? And I'm using this tangent line approximation to come up with a point that approximates the real point on the solution. So we're going to continue doing this. Now I'm going to use 0.5, 0.5. I'm going to take that to be a point on my solution and do the exact same thing again. Instead of using 0, 1 as my initial condition, use 0.5, 0.5. And you do it again. So let's see. K is going to represent our step. So let's say step 0. T sub k, y sub k, that's the point on the curve that we're working with, or the approximate point on the curve. So our first one was 0, 1. That's the initial condition. We calculated the slope, dy dt, at this point, and that was -1. Delta t, we used 0.5. We just moved 0.5 over. And then we calculate delta y, right, by doing slope times delta t. Okay, so this ends up being -0.5. Then you use that to get your next point. So step 1, okay, delta t was 0.5, so I add 0.5 to my previous t. Delta y is -0.5, add that to your previous y. Then calculate the slope at this new point, 0.5, 0.5. So remember the equation was t minus y squared. So what's my new slope at 0.5, 0.5? 0.25. So yes, 0.5 minus 0.25 is 0.25. Then delta t, we're going to continue using a step size of 0.5. So this is always a constant, and you choose it. Okay, delta t is something you choose, or you're told in the problem. And then we calculate delta y by doing slope times delta t. 0.25 times 0.5, 0.125 is my delta y. And we go to our next step, step 2. Calculate your new t comma k. So t used to be 0.5, add delta t and you get 1. Y used to be 0.5, add delta y and you get 0.625. And we have another point that should be approximately near our curve. So y of 1 should be approximately 0.625. So we're going to keep doing this until we get an approximation for y of 2, because that was what I asked you to do. All right, so calculate a new dy dt. 1 minus 0.625 squared. .609375. Did I do that right? 0.609375. So here's my new slope. My delta t is always going to be 0.5, or whatever is given to you in the problem, or whatever you decide it should be. Delta y is slope times delta t. So we do this times 0.5, 0.3046875. Move on to step 3. Calculate your new t sub k and y sub k, your new point on the approximately close to the curve. Okay, so t was 1, add delta t, 0.5, 1.5. Y was 0.625, add delta y. Plus 0.625, 0.9296875. Calculate your new slope. Use my graphing calculator. Yep. So t 1.5 minus y squared, 0.9296875 squared. So here's my new slope, 0.63568. So when you're writing these down, like what I do is I don't write down every single decimal, but when I use the number in my calculator, use the real number with all the decimal points. Yeah. Or you could store it if you need to. Okay, so delta t is still 0.5. Delta y is your slope times your delta t. So this is my slope, this whole number. Multiply that times delta t, 0.5, and we get 0.3178. One more step, because my t was 1.5, add delta t and I get 2. So that's what I'm interested, the value of the solution at 2. So my y value is going to be my previous y value plus delta y. So it's going to be 0.9296875 plus previous answer, 1.25 approximately. And that's where I can stop. I don't have to calculate the next slope because this is what I wanted to know. I wanted to know an approximate value for y on the solution curve when t is 2. So y of 2 is approximately 1.25. Would you say it's way off? Yeah. So how did you find the exact solution?
I was just saying our guess why.
Oh, yeah, so our guess of 0.6, right, was way off. Yeah. That's Euler's method. Make small steps forward. Each time use the slope, the tangent line, as an approximation to the curve. So I'm going to have you try, there's a whole bunch here. Let me do one step with you, because I think another picture would really help. So we know that y of 0 is 10 in this picture. Actually, I'm not even going to draw it on the slope field. So I'm looking for my solution curve y of t. I know one point on the solution curve for sure is 0, 10. So I put that down here, 0, 10. And then I want to know where my curve goes. And the only thing I know about it is the slope of the tangent line. So the slope of the tangent line at that point is what? 8, right? You plug 0, 10 into the formula for dy dt, because dy dt is the slope of the tangent line, and you get 8. So I'm going to draw like a steep tangent line here with slope 8. Okay, so then I'm going to use that tangent line because my curve might look something like this. That's a bad picture. Right, my curve, I have no idea what it looks like, but I know that this blue line is tangent to it. So my curve might be something like that underneath, or it could be above, right? But I'm going to go over by some small step, 0.5, and I'm going to use the blue line to approximate the green line, right? I know that tangent lines approximate the curve as long as I'm near the point of tangency. So what I really want to know, what I'm trying to figure out is an approximation for that value. I want to know the y value on the curve at 0.5. But there's no way of knowing that. All I have is the tangent line, right? So I'm going to use the tangent line to approximate it. So instead of getting the point on the curve, get the point on the tangent line, and we'll say that's close enough, right? So what I did is from my initial point, I went over by 0.5 and up by some delta y, right? And I know the slope of this line is 8. So I know delta y is slope times delta x, which is going to be 8 times 0.5, which is 4. So if delta y is 4, then what are the coordinates of this new point? For 0.5, because I went right 0.5 for my initial point. I went to the right 5, delta x 0.5. And I started at 10, and my delta y was 4. So go 10 plus 4, and that gives you 14. So I would say that y of 0.5 is approximately equal to 10 plus 4, which is 14. So that's the picture of what Euler's method does. It says we're looking for points on the curve, but we're going to approximate them with points on the tangent line.
It's like it kind of like varies case by case. It's not like it's really good.
Yes, it could be really good if the tangent line is making a good approximation to the curve, or it could be really bad. And the larger your step size, the bigger the error is going to be, right? Because the closer you are to the point of tangency, the better the approximation. So a step size of 0.5 is actually pretty big. So we are going to have an error at each step, and those errors can accumulate. And that's a big drawback of Euler's method. To bring the error down, use a smaller step size.